I think
Okay, I think it should be recording now.
that started.
Okay, great. So yeah, so this is the first question here. We are given a list of characters in sorted order, and we're also given a target element. So the idea is that we want to find the smallest element which is greater than the given target, right? So as an example, if you look at the first one here, your target is A. So the smallest element in the list, which is larger than A, is C, and that's what the answer is. The one caveat there is that if the target is Z, like then the list, the algorithm also wraps around. So if your letters are A and B and you're trying to find Z, then you can just, circle back and the answer would be A. Make sense?
Yeah.
So the other, yeah, so that's pretty much the idea. I have tried to solve the question, but there are a few caveats. We can talk about that. But if the question is clear here, any questions on the question here? All right. So anyone want to share their approach?
One I think could be like you can convert it to their ASCII codes
Okay.
and then apply the binary. I mean, convert target also to the ASCII code and apply the binary search. Once you've
Right.
regarding the wraparound case, if you reach the end of the array, just check if I is greater than n. Then in that
Sure.
case, you return the first element.
Return the first element. Yeah. Makes sense, right? So the fact that in the question we are given these hints, right? It's a sorted list, and
Yeah,
you
exactly.
have to actually search. Uh, it's a search algorithm. So the moment you see sorted, it's kind of a hint towards binary search, right? So that's I'm not sure who was. I can't see the person who's talking, but yeah, thank you. So this was the similar idea I had, and I guess even in the discussions that would be the case. Does everyone see the idea here? So we are just doing a binary search on the given array, and to handle the conditions of wraparound, there will be additional, if then if else conditions, but it's a pretty straightforward binary search. I mean,
Are you saying is binary search is the only efficient algorithm for this, or is one of the approach?
that was one that I could think of. I mean, linear is of course like order of n, but binary search would be a log n. But is there any other idea you could think of here, like which would be better than log n?
No, I'm not saying about that, because what I'm saying is if the letters are only A to Z, so
Right.
they are not big, right? So are we going to have bigger? Oh yeah, I think it is. There might be a lot of duplicates also in it.
Yeah, right. So that was another thing I wanted to come to, right? Like there can be duplicates. Like the question says it will have at least 2 unique characters, letters, but I mean, in general, given the whole list, it can be duplicates.
So one thing I was thinking, like if you have an array of 26, and just keep on adding, incrementing the counts of each and every alphabet. So it might be a linear search. You don't even have to do a sorting there.
Yes. Array is already sorted.
Sorted.
Yeah, but if it's a big list and
Yeah.
you just go through each, because anyway you have to go through. Yeah, even if it is binary search, yeah, you'll have to go for log n. Yeah.
I think sorted they gave intentionally to apply binary. Otherwise,
Right.
had it been like random, no, we could have gone the process what you're mentioning. Like,
Yeah.
I mean, then we won't be using the benefit of that sorted.
Right, and also it comes also, yeah, I agree with the sorted point, and also the fact that it's not just like there can be duplicates, so the list can be really long. If it was a fixed number, then it's like, just a constant time kind of just go through the whole thing and do it.
And they have given the constant that the length for the array is 10 to the power 5.
Okay. Yeah.
Oh, yeah, yeah.
Oh yeah, right. Okay, thanks. Yeah. So,
One other approach would be to, I mean, you can start at the zeroth letter itself,
yeah.
and you can compare zero. I mean, so if you heard about um, uh, doubling and searching, have you heard about? I mean, there's a protocol as well. I mean, in TCP, you use for finding the optimum size that needs to be sent as a packet size. So you actually double it and find it out. So here also you can start at 0 and 2. If you can search for, I mean, the least. So you can
Right.
go on doubling it and find a particular range. Then in that range, you can do a binary search.
You're saying that, what do you mean by doubling?
So like,
So,
can we take an example here? The first one.
I will try to tell it something like this. So let's suppose if there are so many letters.
Yeah.
So I mean there can be duplicates as well.
Mhm.
So you start with I mean, let's suppose take it as C itself. You start with 0. I mean, compare it with that letter. If it is greater than, I mean, if it is greater than that, you try to go to 2, 4, 8, something like that.
Oh.
And
Okay.
so in that way, you will actually try to get a bound in between where it is actually trying to lie.
I see. Like, I think you are trying.
That is also a binary search, the expansion binary search.
Yeah,
Yeah.
no, I'm trying. Yeah, but you can. I mean, that would be. I'm saying lesser than. I'm guessing so. I'm not sure. That time complexity might be less than this one.
No,
Because
time complexity will be same for both.
Yeah. Essentially, if I understand this right, essentially we are just following a little different approach of creating those intervals, right? In binary search, we are splitting in half every time. And in what you are saying, we are just doing like 2 jumps, or 2-letter jumps, something like
yeah.
that. So, yeah.
Can we see the code?
So one is the compression, and you are saying that the expansion. So
Right.
both are same.
Both are similar. Yeah, right. Yeah, but in general, it's a good, like, idea maybe for other problems or to think around. But I think for this one, it will be pretty, in general, it will be pretty.
Yeah, the expansion binary search is useful when you have a infinite stream.
Right. Okay.
Then you don't have the end limit.
I see. Okay. Not sure. Can somebody post the link on Slack for joining?
Can you can we see the code, the binary search?
Yeah. So I have one caveat in my code. So if I were to share, let me just bring the code here. I think, so I tried this solution, which kinds of works, like if I over the test cases they have, but I'm thinking that maybe if I have duplicates, I have to look into it more. So I'll just delete this one. So this is what I have here. Right. So this one, I just do plain binary search, right? But this is where I'm trying to handle the wraparound cases, that if I reach, so this is like pretty standard, right? And then when I come here, I'm trying to handle these cases, that if I'm given a list, CFJ, and target is K, that means eventually I'll run into a situation where I have to jump out of this loop and this element is not even present. So in that case, I check this condition and I return the first letter because it's a wraparound case. And similarly, in the case where I hit, like J, in that also case, I have to wrap around. So this code,
So let's say if we have duplicate, can't we go for
yeah,
some modulus operation? Like the moment we reach the end of the array, we'll divide that by the entire length of the array. I mean mod, it will make you reach again to the starting point.
oh,
Yeah.
you're saying for this case?
Yeah, just do a
No.
modulo of letter sizes. Yeah.
Yeah, exactly. It will, the moment you reach last, you divide it by mod, you'll get you back to the first one.
Modulo of,
Your start, start with modulo of the letter size. Yeah.
Yeah.
okay. Oh, so you're saying I don't even need to do this?
No, here you should do. I mean, in that case, linear. I mean, order of n it will be like you are. I mean, let's say if here you don't have any duplicates, right?
Right, right.
The moment you have duplicates, I'm not telling to use binary search. I'm telling just each time you divide the length by the mod operation, so that the moment you reach the end of the array, I mean, let's say you want z is there, so greater than z will be a. You want a for that, right? So for that you need to come to the first index, and
Right.
for that you need to divide by mod. But that will be order of n. But duplicate will be covered in that case.
Duplicate will be covered. Yeah, I noticed that in this case, I probably, didn't think of at least while coding duplicates.
Yeah. But here I think it's already they have given that.
Yeah.
So,
Yeah, but I think this is a good way of showing to the interviewer at least what she has written, wraparound cases. So you can explicitly show there saying, this is what I'm handling about this.
Right.
Yeah, I think this is a good thing to show there. Then you can talk about the one what Shashank is saying.
Right, sure.
Yeah.
So the way how I actually think about that, so here in your while loop, so when you actually hit the else case,
Yeah.
so that may be your potential, that may be a possible answer, right? Because that is the largest element.
Mm-hmm.
So I was actually keeping the track for that one. And when I'm coming out from the loop, and I initialize that with some invalid value initially. And when I come out from the loop, I check that if the value for the answer is valid, then that is my answer. If it's invalid, then it's the first item for the array. Yeah.
So you're adding more like logic here.
Just one line of code to keep the mid.
Right. Yeah. I mean.
So you are going to store something when in the else case. That is what you're saying.
Yeah, what I'm saying that when we hit the else, so that we know that for sure that is a possible answer, because this value is now bigger than my target.
Mm-hmm. Okay.
Yeah.
So would that n equal mid, or in some case that n could be something else?
I mean, as I was thinking of examples, I could think of in general, let's say I have CFF, right? And I'm looking for, I mean, essentially, I was thinking of the case where I hit the mid, but the next character is also same. So how do I handle that case, right? Should I skip that or something around that? But so I believe there are a couple of cases that can be handled here, maybe by some,
No, I'm asking by the time we break out of the while loop, is it n always equal mid, or n could be something else? Because someone will say, have a variable to keep track of mid, right?
No, I think the idea there wasn't, it was something to do with handling duplicates, right? The idea before, are you referring to that?
No, I think somebody was saying that he'll keep a variable.
Right.
In the else loop, and the else statement keep track of the mid.
Yeah, some potential candidate, something he was, I mean, name I don't know, but he was speaking. I couldn't even get that clear. If you can explain once more.
Yeah, so let me try again. So when we check that, so if target is, we know that the middle element is bigger than target.
Hmm.
So that we know that may be possible, that this may be our answer, right?
Yeah. Hmm.
Oh, right, yeah, okay.
So we store that. So we keep a variable outside the loop and initialize that with some invalid value, say like -1.
Yeah.
Okay.
And then every time when we found that, okay, this is a possible candidate, so we actually update that. And when we come out from the loop, so at that time we check that if we have a valid value in that, that is our answer. If we have an invalid value in that, then wrap around and return the first element.
Right. I think you're
Okay,
talking
yeah.
about this case, right? Like if you have CFG and your target is E, now your middle element is F,
Yes,
and that itself can be your answer, right?
yes, yes.
So you're trying to actually save that and
Right.
Yeah.
Actually, he's not trying to break there, he will continue in that loop, but only he's updating that value in the else.
yeah,
Yes,
he's
exactly,
maintaining
yeah.
that value,
That's right.
right?
Yeah, that's true.
Like
Because we are not sure whether this is the answer or not. That I'm just actually guessing that is a potential answer, right?
Absolutely, yeah. Yeah, makes sense.
Yeah.
makes sense.
And can we, is that wraparound case necessary? Is it possible to test it at the beginning itself?
The wraparound case, like here itself.
Yeah,
I
before doing the binary search.
I believe there should be, like the way I wrote this code was I wrote this one quickly and then I thought of this, but I believe there should be like the one that explained, right? Saving the candidate solution and handling even this case above itself in the while loop. That is a possibility.
Okay.
I mean, I just noted that the question was binary research. I started doing it and then, yeah. This is not the best way to write it, but yeah.
So that's okay, yeah, that's fine.
Anyways, we have to go till the end, right? I mean, is it possible to do it at the start?
I don't think so.
Yeah, because
Yeah.
at the start, if it's the same value, start and end, so it means it's only single value there, right? The letters are only one character.
Yeah. In
I
that,
didn't understand that. Why you have to
Oh.
do it at the start? I think this is the right way to do.
Yeah.
I was thinking of checking the last value if the target is greater than the last element. So that means that is the wraparound case. We can.
Oh, you were just trying to avoid like even this logic, right? So you were just saying if here itself, if we can say, because it's a sorted one, I can just compare like target is greater than
the last element.
the last element.
Oh, okay.
Yeah.
Yeah. So that's a different condition there. Okay, no problem.
Yeah.
But
Yeah.
That's
that
a
will
good thing to
avoid-
add. Yeah.
Yeah, like last element basically.
That's an optimized way of doing it.
Yeah.
Yeah. Okay.
Yeah, I think this question in general might be very easy to spot, like binary search, but handling all these cases might be an interesting way to
Yeah.
get the
It's very
coding.
tricky. Yeah.
Yeah, it can
No,
one can get easily confused.
If you have that condition, then I think there's no need for that wraparound case. So once you exit the while loop, you
Okay.
can just return end. End will always be the value greater than the given value.
Oh, I see what you're saying. Yeah, it will handle this case and then even this. Okay.
Yeah, that is true, but actually, if you show this value to the interviewer, he'll be impressed, I would say. Yeah.
Yeah.
This
But
one.
it's good. Yeah, the run case. But anyway, when you're solving it and make it more optimized, then what I think Chandra was saying also.
Sure.
Should be best way to do.
Yeah. Okay. All right. So are we good with this question? Okay. Taking that as a yes. So let's move to the next one. So I'll do the third problem and then I'll pass on to Uday for the second one.
So can we do in sequence, please?
We can do. I just have to switch the hosts.
Generally, how we actually do that.
Yeah, right. I was just trying to avoid the shuffle, but if that's what everyone prefers, we can do that.
Actually,
In
you
the
can
record,
just stop the sharing your screen and he can share it. You don't have to change
Okay.
the host, I think. Yeah.
Okay, perfect. Yeah. So Uday, you can take up.
1 minute. It is asking for
Oh,
sharing permissions.
yeah. Yeah, I made
You
it.
have to make it also. Okay.
Yeah. Yeah. The second question is this. So basically, you are given a string and you are given a list of pairs. I mean, the pair will be containing an integers. So the question is, you need to find the lexicographically smallest string by swapping. I mean, you can swap any number of times at this indices. I mean, you can swap the characters at this integer pairs. So basically, if you take this example, there's a given DCAB is a given string, and there's a list of pairs. So 0, 3 is one pair and 1 is to another pair. So the pair just consists of the indexes, and you can swap characters at these indexes and any number of times basically, and you need to form the smallest, I mean, lexicographically smallest string that is possible. Hope the question is clear.
yeah.
Yeah. So if you take this example, so DCAB 0312. So you can, I mean, so only these you can swap 03, and I mean these 03 you can actually take it as a one set kind of thing, and you can form the, since you need a lexicographically shortest one, you can form the lexicographically shortest string of this one, I mean, for each pair or something like that, and you can replace it in the original string to form it. So you will replace A and D and B and C in this first example to form the smallest one. But if the number of pairs actually increases, so those actually try, I mean, before I get to the solution, if someone has any approach, you can.
No, I was
actually
thinking, like when you said the pairs, you just have the indexes of those, the pairs are the indexes in the string, right? So you just swap on, and like if you want to find something lexicographically small, you just look at the pairs.
I just want to make one comment before we get into solution that might help, that we can repeat like, any pair.
So see this pair, actually the second one, 03, 1, 2, 0, 2. So you can actually swap 0 with 3 or 1 or 2.
Yeah, I was trying to point to the third example, where we are actually using the pair 0, 1 twice. So, I mean, I was just making that comment that we can do that, right? Like we are swapping 0 with 1. It's not like one pair we can only pick once.
Yeah, that is mentioned there in the question, that you can repeat and you can execute that any number of times.
Sure. Yeah.
Okay, yeah. So in this example, you can either replace 0 with 1 or 0 with, you can swap with 0 with 1 or 0 with 2.
Okay. So in that case, you can do anything there with the whole string in the third one.
Yeah, in the
you have
third
all
one,
the indexes. Yeah. Okay.
Yeah. Similarly, here also you can actually swap a 0, 1, 2 as well in the second one. I mean, if you see it in the closed one, 1 forms a loop with 0, 1, 2 forms a loop, and again if you combine 3, 0, 1, all 0, 1, 2, 3 all form a connected thing.
Oh, I see. Okay.
So this is what you have to find first, right? Okay.
So one
Yeah.
approach, actually you guys are also leaning towards that. What I would like to say that in this case, like since we have connections, it is kind of a, like, connected component. Unfortunately, this screen is already showing me the solution. So let's not think about it for the time being. The other thing which was saying that you can swap it any number of times. If you have connected things, and if I can swap like, multiple times, basically I can perform a bubble sort, right? Think about it, to sort the entire string, right? Does that make sense? Because I have all these 3 or 4 things connected. Like if you say example 2, everything is connected in a way. So it doesn't matter how I do, but I know I can swap anything with anything eventually, if I perform like, enough number of swaps. So basically I will perform some bubble sorting, like, and I can get to the sorted output.
So yeah, the thing is only fixed number of pairs actually form a circle or loop kind of thing. If you take the first one, only 0 and 3 you can swap. You cannot swap 1 with 0 or 3.
Right. So I said like connected components. So
Yeah, true.
you have only you have 2 different connected component. Example 1, right?
Yeah.
So you could swap 0 and 3, right?
Yeah.
And 1 and 2 separately.
Yeah.
Right.
Yeah, like in example 2, there is only one connected component.
Right. Even in, I think example 3 is also similar, I guess.
Yes.
Only one connected component.
Yeah. So that's the intuition. And now please proceed. Like I know, like we are all leaning towards the same thing.
Can I just one question about this connected component? So in example 2, are we saying that we are forming a cyclic group? Somehow I'm not able to capture that part. So like we can swap 0 with 3, but we can't swap like 2 with 3, right?
But then you can swap 0 with 2. Think about it. You swap 0 with 3, but then you can again swap 0 with 2. So if you want to bring 2 to the top, you can, right?
Okay.
And then 1 also. I can do whatever I want once
I see what, makes sense.
So I think what Roger is saying is first find the connected ones.
Yeah.
Make a list of that, and then you sort them separately, and then add it to the string.
Mm-hmm.
Yeah, that is the
Yeah.
approach.
So the idea is just to find the connected component, and after that just sort it, because you know that if they are in the same connected component, so anyhow you can sort it. What Roger just mentioned, that don't worry about that, how and what steps you will follow.
Sure. Yeah, I didn't capture that connected component when I looked at it.
And then you have to merge also different connected components. And I think that's what Uday will explain shortly, I guess.
Okay, so if you want to look at the code, so initially, till this part of code, let's just union find itself, and let's forget about that for now. So initially I'm just finding the connected components using that union find itself. So if I'm merging 0, let's take example 2 itself, 1 and 2 and 0 and 2. I'm taking one of them for every pair. I'm taking one of them as root, and I'm connecting the other element to that root, something like that. I'm assigning root to every element, and I'm merging those pairs to find the connected components actually.
So we can use DFS also for getting that connected components.
Yeah,
you can use an island. Yeah, you can go through a BFS way. Yeah, but he's doing it the union find. I think that is the more efficient. Yeah, I'm not sure.
If you need to do DFS, you need to find. You need to form all the edges as well. Actually,
Yeah,
but
we'll with
Can we actually
yeah.
draw the graph for this or no?
I mean, okay. So for this 0 and 3, I'm making 0 as one of the root. I mean 0 as parent for the 3, and 0 is the root itself for the union find. And 1 and 2 came. I'm making 1 as the root. Yeah. Now again 0 and 2 came into picture. So I'm making root of 2, that is 1, point to 0. I mean, I'm not able to draw it here.
yeah.
So something like this. Hope this is clear.
Why did we choose the 1 to be the pointing to the root of 3? I mean of, yeah, the root 0.
Okay. So when you're merging 1 and 2, you understood, right? 2 is
Yeah,
pointing to 1.
yeah.
Yeah. So when 0 and 2 came into picture, you need to find the parent of 0 and 2.
Okay, so 2, it was already 1, so that's why 1
Yeah.
would point to 0.
Yeah. So 1 is again pointing to 0.
Okay. So once
Yeah.
you find this union, right?
Yeah.
How do you start searching actually or combining?
Yeah. So so for every index, I will try to find its parent, and I will for every parent, I'm creating a list. I mean, for every connected component's root, I'm trying to form a list. So if you so for I from 0 to the string length, I'm finding its parent, and I'm seeing if there's a list for that parent. If not, I'm creating a list and I'm adding that particular index to that list of list of vertices in that connected component. So I'm making that parent as the indicator to find that list.
Okay, so let's say if we start with, let's say 0, let's make it like a table and say.
Yeah, here, okay, let's take one more actually.
We can actually start a new line, no? Or you taking another one? Yeah.
Yeah, so these are two connected components. So I'm iterating from 0 to 7, let's suppose here, this is the case. For 0, there is no list. So I'm creating a list of 0. And for 1, I'm finding out the parent, which I'm getting it as 1 again, and I'm in 0. I'm adding it to that list. For 2, similarly, I'm finding the parent as 0.
Okay.
And for 3, similarly 0. And when I'm going to 4, I'm not finding a list, so I'm trying to create a new list with 4. And similarly for 5 and 6, 7.
Got it.
Yeah. So this is kind of a map kind of thing. So I'm iterating over each list and trying to sort characters at that index, and I'm replacing it in the original string.
So you take the key of any of those lists and you try to substitute with the list it has, right?
Yeah, for every connected component, I'm having a root, and using that root, I'm trying to form that list.
Okay.
Of what are the vertices in that connected component.
Yeah, I understand the creating the list, but I didn't understand like how to, what to replace and how, you know.
Okay. So after you get the indices, you just need to you can create a new array with this characters at this indices and sort it, and you can replace it in the original string or create a new string.
Okay.
So you can take a new array of size 4, and you can keep the characters which are in the original string of 0, 1, 2, 3, and you can sort it, and you can replace it in the original string.
So let's say I start with 0, 0 you can replace with 0. So you replace 0 and 1, right? And then you replace 0 and 2.
Well, let's take it as this one itself. Suppose 0 is B and 3 is C.
Okay.
3 is D and F.
No, it
A.
was A and okay.
Yeah.
Okay.
Now let's suppose this is here Z, and let's suppose this. Yeah. So for this, you can actually take all those indices. So for at 0 you have B, and 1 is F.
I think it says it's C for 1, no? I mean,
sorry,
whatever,
1,
according to the
yeah,
example.
Yeah, 1 is F and 2 is, I'm just according to the drawing, I'm doing it.
You have 2 Fs though. That's why.
Yeah.
Oh, okay. So you can repeat, right?
Yeah, it can repeat.
Okay.
Z, G and R.
Yeah. So you can sort this one.
A, B, B.
Sorry.
B, yeah.
F, yeah.
FG.
Yeah. So you can so you know the connected components indices as well. So you can copy the characters from the sorted string to the. So you can actually create a buffer with those many characters, and you can replace it there. So
okay, so
after
it's gonna
sorting
be
the first,
A, B, D, F, F, G, R, Z. Cool. So by sorting this list, you actually get the result that you want.
Yeah.
Cool. Thanks for clarifying, man.
Something like this.
Cool. Thanks.
Yeah. So this is what I'm doing again. So I'm taking every list and I'm copying the characters to a temporary array, and I'm sorting it. And since I know the connected component indices, I'm replacing it again at that string.
Yeah, this makes much more sense now. Thank you.
So in your union find, you are using another array also, R something, right?
Yeah, so basically I'm using, so if you are actually in union find, when you're trying to find the parent or doing union, you need to call find again and again. So that might form a skewed tree. So when I'm joining two trees, I'm using a union by rank. So those are the ones. So P is the parent and R is the rank for that index. Rank means you can actually treat it as height itself. Okay, this one should be 1. Yeah, you can take it as 0 as well. So basically when I'm joining two trees, I'm comparing it by the rank of that particular tree. I mean, it is basically height itself. If it is a smaller subtree, I'm pointing the smaller tree's parent to bigger rank's tree parent.
Yeah. Okay.
Yeah. Yeah. So any doubts in this approach?
What about time complexity?
Time complexity. The union find is a tricky one actually. I mean, generally it is since you are merging by the rank and these all, it's generally O of log n. But so I'm using a so I have optimized. I modified the find code as well so that I'm compressing the tree as well. So this actually, if you are calling it from n times, the tree actually compresses actually.
By height, yeah.
Yeah. So if you are calling for the particular tree, the tree, every subnode in the tree actually points it to the root itself at the last.
Yeah.
Yeah. So it actually comes out to be amortized O of n itself. I mean, that you can debate, amortize it. And this mapping and set that will take around n log n, I would say. And the sorting also, I'm using an arrays.sort. So that is also, you can say it as n log n itself.
Okay. Yeah.
So overall, it is n log n itself. I mean, even if the path compression is not there, union find itself is n log n mostly.
Okay.
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 Yeah.
Thanks, Uday.
Yeah.
So let me switch to the third one. Everyone see my screen here?
Yeah.
Okay. So the third question is the snakes and ladders game. And I mean, I guess everyone would be familiar with this, but just in terms of the problem description. So you're given this, board configuration, and you start from the, the first square, bottommost, and then you have to get the last position on the board. So here you have to start from 1 and you have to get to 36, right? So the question is, what is the least number of moves required to do so, right? And so we can take an example. So here, this is the configuration. This is how the board is represented. So -1 is just like you stay where, that's the position where you are. For any other thing, like for example, 15, that means it's a ladder taking you to square 15, right? So this is a 6 by 6. So 15 would be like, and the other thing is it's just the way the board is set up, right? It's like directionally, it alternates, right? So if you start from here, just like a typical snake ladder board game. So you start from here and you go towards the right, and then you start for this row, you start from right and you go towards the left. So in this configuration here, when you are at second square, essentially you're jumping to square 15, right? So which would be this one here, right? And similarly, so something like this, here you're going back. So this is like representing a snake. So it's taking you back from square 17 to square 13, which is this one. And similarly, 35 this square. Does the configuration make sense? Like everyone understands how that's represented? So the question here is how to get, if you start from the first square, how to get to the last one, and what's the least number of moves in which you can do so. So
I
in
don't
this,
understand how's 4 when it comes up to 5 actually.
Yeah, we can. Like the answer, how we got 4?
Yeah. No. I understand all that, but like how's it 4 when I try to move myself and it's kind of like 5 moves.
Okay, we can just walk through it quickly. So we start from the first one, right? And we go to the square, right, which is 1 move, right? Yeah. And that takes me to this here. Mm-hmm. From here, I make another move of 2, right?
Oh, okay, that's 1 move. Okay, I got it now.
Yeah. All right. So it's not like number of steps there. It's like 1 move can be. Yeah.
Got it. Thanks.
Yeah. So from here, we are going to this one, which is second move. And this takes us back to this square. And now from here, we can go 1 step, which is third move. And that takes us to 35. And from here, finally, we take 1 more move and we get to the destination. So it's like total 4 moves. Everyone understands this, like how we got to the solution, and any questions on anything till now? Okay, so yeah, anyone has tried to solve it or any ideas? So we have to return the minimum, how we can reach destination in minimum number of moves, right? That's the goal. So how would you go about that?
Well, I have not tried, but
yeah,
the last keyword you mentioned, that minimum, so that's ring the bell in that we should go with BFS.
Right. Yeah. So this is like we are trying to traverse this kind of a structure. So yeah, like you said, it's the least number of moves. So BFS is has that characteristic, right? It can allow you to reach destination in least number of steps. So that's kind of the hint there.
DP can't be there because of that hint. Could be, no.
Depth first, in my view, you can follow depth first, but it may not guarantee least number of moves, right? Because you may traverse a path and then you have to, come back. So.
No, I was asking for DP. I mean.
Oh, dynamic programming?
Yeah. I mean, just thinking like if.
So dynamic programming.
Like we used to know from top left to bottom right, all this like in a grid, the shortest path to reach from one into other.
Right. So in dynamic programming, the way I look at that is we usually need some decomposition of the problem, right? Yeah. And then we need that overlapping characteristic in dynamic programming so we can save the results. But like even first step, how can we think of this in terms of, maybe you can elaborate, like I wasn't going that route, but does that,
no, I was just asking.
Like with dynamic programming, we would need to do that.
No, I'm also not confirmed, but just by seeing that least number of moves.
No, least is there, but the fact that it's not really a divide and conquer, as I see.
And when we move, so I don't see that there are choice. We do have choice, right?
Right. Yes. So for every position, right? It's like when you roll a dice, you essentially have 6 choices, right? You can go to any of the next 6 steps.
A question. If we go up a little bit on the picture, can we actually have either an array with 36 a size of 36, and then for each field we actually put the pair of I and j, a row and column, so that instead of having this edge cases when it goes left or right, to actually
we always have that bound, right? We can always check that.
Yeah, so we just kind of like go sequentially, and take the I and j whenever we need it from this.
So for this board, you're saying the configuration, as an example, it will be like 2,15. Is that something?
No. So it's going to be an array with index 0 to 35, which is 36 elements. And for each element, it actually holds I and j. For example, it holds in the beginning for the zero element, it holds I is equal to it holds 5 and 0, because row is number 5 and column is number 0, so 5 0. And then for 2 it holds 5 1 and then 5 3, etc. So as we go now sequentially, instead of going through the matrix itself, we go through the array, and we take the I and j from the array, and then we take the value of the matrix itself, and then see.
Okay, so the value at 5,1 element in the array would be.
So you take those take those row column from that array, and then you get the value from the original board. And then if it says to go to 15, then you actually, instead of going to the board, you go through the array itself and take the IJ from there.
So you are saying we need to create another array and put all these information in it?
Yeah. Put the indexes of the field.
But this is going to be an extra work, right? So
I mean, it's going to be extra space, but
yeah, we can find it on the fly, right?
Yeah.
Have a function do that.
Yeah, no, I understand. But instead of having a function to actually know exactly where it is.
Okay, yeah, just for explanation purpose. Yeah, that's good. Yeah, okay, got it.
I am not sure if that approach will totally work, because if you take a sequential array, right, and the example what you have given, like 5 1 has 2 with a ladder which takes you to the 15, right? So suppose 4 0, which is number 12, has a ladder which takes you to 35, suppose, right, directly. And then you can take a second step which will take you to 36. So there'll be only 2 steps, but to get to 12 with a sequential array, you might have to make more moves.
Sure.
No, I get it. Yeah, but you start from 1, and then 1 is actually gonna branch out. For example, 1 plus 1, and then 1 plus 2. So that's how you're gonna count the moves.
Yeah, I think what you're suggesting is just a way of representing this board, ladders and snakes, but eventually you are still, like, it's not a sequential way. You're still saying we will explore using BFS.
Yes. For each field, we'll explore x plus 1, x plus 2, x plus 3.
Yeah.
So on and so on.
Yeah, I think he's alluding to how you represent board and these jumps and snakes. Otherwise, overall algorithm remains like BFS. Yeah.
Yep.
Agree? Yeah. So yeah, so this is some similar idea I followed, right? So you start from the first one, you have 6 possibilities. And even before going there, like, it's BFS, that's something we see here. And that kind of gives the hint that the data structure we use for breadth first, because we have to evaluate all the choices at every level, we use a queue data structure, right? So those were the things that I started with. And then coming to the discussion we had just now about how to represent the board, I actually looked at one of the solutions, and I mean, I liked this way, but what you presented, somebody who was talking about 2D array, that can be another way. So in the example that I looked at, they were actually transforming this whole thing into a one-dimensional array. and you can actually store the position, like this one is leading to 15 and so on. But in terms of algorithm, it comes down to that you start from the first one, you have your 6 choices. So you actually add all 6 to the queue, and then you try to evaluate each of them based on the configuration. Maybe I can show the code if that would help. Yeah, so I just have a structure for my queue. Now, since I have to return the number of moves, I also have to record my steps, right? How many moves I have been done so far. So in my queue, I'm maintaining these 2 variables. And when I start, this is where I was using that, an existing solution from someone where they converted the whole board into a 1D array. So in this case, in the beginning, you're starting from the left, right? And you're starting from like this row here. So it's this 36 square is row 0, and then you're starting from row 5 actually. So that's why n-1. And yeah, so this is how they are initializing the board. And in every iteration, you are reversing the direction, right? And that will impact this inner J loop, like where I'm starting. If I'm going left to right, then I have to do 0 to n. And if I'm going the opposite way, then I have to start from n-1 till 0. Yeah, so and then the logic about breadth first search. So what I do is I start with, I have a while loop where I traverse my queue. And the important thing here is every time I look at an entry in a queue, I have to make sure that if I've reached the target, right, then I just need to stop. And that's where this condition is coming in. And if this condition is not, if I haven't reached my destination, then I have to evaluate every position starting from the next one, from where I am till the next 6 steps, right? And this thing is saying, like from 1, if I move to 2, or if I move to 3 or 5, any of these things essentially counts as one move, right? So this is where this thing is coming in. And if my board configuration here, like in the example, the way they have given, so if this is not -1, that means it's either a ladder or a snake. So at that point, I update it accordingly, right? And if it is 1, if it is -1, then I just keep it that way. Yeah, and then I just, this is a standard breadth first search. And then at the end, I mean, the moment I reached my destination here, this condition, that time I break and I just return the moves from my current queue entry.
I think one more thing in this is like if you are not able to reach, so you need to return -1, right?
Yeah, correct.
So where that comes here?
Yeah, actually I should do that. Probably I should initialize this moves to -1. Like this is my, actually.
So actually you need to find out if there is a cycle in the graph, right? If there is a cycle, then you have to return -1, right?
If there is a cycle. Oh, I see, like the snake. No, but for that I'm keeping track of visited.
Okay, so then that's fine, yeah.
Yeah.
So if you are unable to complete.
Right. I have to have a way to say, like you said, right, return -1.
Yeah.
I just did the solution till the base case. But
no problem. So because when you said you break the loop, right? So
right.
there itself you can return the entry dot moves, and at the end you can return -1. If
makes sense.
you are using visited, yeah.
Yeah. So if it doesn't hit this condition, right? Yeah. Okay.
That should work.
Yeah. But does everyone like see the concept here, or?
We make sure that it's a minimum move. It will always give you the minimum moves.
Yeah, so this is by the nature of breadth first search, right? Maybe so in the breadth first search, we are evaluating all the choices at every level and then moving on. So your question about whether it will return least number of moves is, the first time we hit that combination, right? I just step out of the loop. The first time I hit my destination, then I just step out.
Okay.
And in this loop, I'm counting my moves, right? So, I mean, there might be answers even after that, but I'm just quitting after I find the first solution. Does that answer? Or maybe if we have time, we can always go over an example.
So for a non-weighted graph, BFS gives the shortest distance.
Right, but in this case, every move is like one, right? Like it's not like different weights.
Yeah, he said
unweighted. That's what I'm trying to say.
Oh,
yeah.
Okay.
Yeah, same thing.
Yeah. So would you like to go over an example, anyone, or this seems good?
Yeah, I think maybe I have to see by myself once this 1D array, because I'm looking at this problem as like a island problem, like a island problem. I'm not sure how many have gone through that problem earlier, but I'm trying to visualize it in that way. But this approach of like having a 1D array and convert this, maybe I have to do it myself. So I'll ask in the group if I have any questions later.
Sure. Yeah.
Yeah, but 1D array was just implementation detail.
Right.
Because if you look at the concept, you are starting like in the bottom most corner towards left, and you want to reach to the top left, right?
Mm-hmm.
And every time you have like 6 edges going from there.
Right.
If you think in graph, right?
Yeah, right.
Yeah. So now, you have fixed number of levels, like you can't go any further than that. And of course you can have snakes or ladder, but that will just convert where you are going eventually with the same position. But other than that, you have like no control. So, all these are your level 1, level 2. And what C is doing that as soon as C has a solution, C is just breaking. So that's why BFS, and when you saw that return the least number of moves, where to reach square n into n. So I remember somebody was talking about DP came to your mind, which is a good thinking. But you should also think about, for any shortest path, BFS should come to your mind as well. And DP was tough because you don't have a relation. Like how would you convert it to a sub problem, and how would you combine the solution, right?
Yeah, directions are not specified like.
Yeah, so this will work, and that's what we are doing here. And it was very nice, actually, code and everything explanation. I really liked.
Thanks. Yeah, if anyone wants to, go over, maybe I can do a quick whiteboard if you want to just. So for example, if we look at -1 here, at that point, my options are, if I'm looking at this one, right? Then my levels wise, like Roger said, it was 6 moves. At that point, it will be, so if you look at the data structure I'm maintaining here, I have a vertex and moves. So if I just write here as an first example, so my possible options will be, I can go to 15 with 1 move, or I can go to 3 with 1 move, or 4, and so on till 7. Right? So this would be like my possible, my queue entries for when I start. And then I start exploring this one, and add its children to the end, and so on. So yeah, the moment I hit the first one, it will be, I'll skip out. Any questions on?
Yeah, I think it's good. Yeah.
Okay. All right. So I think that's what we had for today.
No problem. Thank you, DP.
Yeah. Thank you so much.
Uday.
Thanks for help, everyone.
Thank you.
Thank you very much.
DP.
That's
Thank
great.
you.
Yeah.
Bye.
Thanks. You can stop the recording.
Yeah.